junior in high school. That's Manas. He's a sophomore in high school. And today we'll be presenting our research project, which is where we built both fixed and random effect models inside a program called MATLAB. And we basically compared how each model behaves when we were analyzing medical data. The data set that we used was how texture and color enhancement imaging, which is also called TXI, performs compared to standard white light endoscopy for detecting gastrointestinal lesions. So first, to give basically some background information on meta-analysis. So what is meta-analysis? So meta-analysis is a statistical technique that combines the results of multiple studies to reach an overall conclusion. Instead of relying on one study alone, meta-analysis increases statistical power by pooling findings across studies. And it's widely used across like a lot of different fields, such as medicine, psychology, ecology, and also sometimes used in finance. So in simple terms, it's just basically research about research. And it gives us more complete and reliable understanding of the topic or study. And then after, to give some background information on what MATLAB is, which is, as I said earlier, that's where we conducted our experiment. So MATLAB basically develops and runs meta-analysis models, and it's a high-level computing platform that makes numerical analysis and matrix calculations very easy because you can just type in your program and it'll do everything for you. And it just basically allows us to compute different effect sizes and variances in different studies, and also stuff like confidence intervals and weight for both models. So yeah, that's what MATLAB is. So next is what we wanted to get done with this experiment, our research objectives. So the main goal of this project was to apply both these fixed effect and random effect models to the medical data set that I explained earlier, and basically compare the results to see the differences between a fixed effect model and a random effect model. And we want to see not only which model gave higher or lower effect sizes, but also how the variability between the two results was influenced. Oh, it just turned off.
It's back.
Okay. Oh, I picked the wrong button. Okay, sorry. Okay, so next is like our preliminary analysis, which is just basically some information we did beforehand before conducting our experiment. So for the data set, we used results from multiple studies. Our primary one was from a website, which compared two imaging methods, which was white light endoscopy and TXI, which enhances texture and color. So then we applied both fixed and random effect models to perform meta-analysis on those data sets. And our goal at this stage of the experiment was to prepare the data to use the meta-analysis equations on inside of MATLAB. And then lastly, like what, or not lastly, but what our fixed and random effects, because I've been saying that a lot. So basically a fixed effect model assumes that each group of data is by itself, whereas the random effects, it assumes that all the groups are a part of a bigger group, so that there's some sort of error that you're not accounting for, but that's not your primary focus. So that's what it is. It's just basically fixed effect model is a group by itself, and random assumes it's a part of something bigger. So there's some differences.
So how did we conduct the research? So first thing we did was that we used another effect models, and then we found the standardized mean difference of our data. Then we computed t-squared. T-squared stands for tau squared, and it is the variance between studies. To calculate t-squared, we used the equation. Oh, what is that?
We're clicking wrong.
Oh my god, I'm clicking back to here. Okay. We use that equation, t-squared equals q minus df over c, where df is 1 less than the sample size, and q is the sum of the weight of each study times the squared d of each study minus the whole square of the sum of the weight of each study times the sum of d divided by the sum of the weight of each study. Additionally, c is the sum of the weight of each study minus the sum of the weight of each study squared divided by the sum of the weight of each study. Using t-squared, we were able to find the variance between the studies, where we use Vy to find the within study variance and add T to it. And then we use the variance to find the sum effect over the scientific study. Then we did similar steps to find the fixed effect models. We found the standardized mean difference, and then we found the variance for D and the square root of said variance. Using those, we calculated J. J removes the bias in D. Instead it hedges D, the means is unbound. Similarly, we use DF here, which remains as one less than the sample size. Using J, we find hedges D, which is representing our standardized mean difference. And then we find the weight and sum effect of the study. These steps overlap for both fixed effect and random effect models. We find the weighted mean, and then we find the variance and the square root of the variance of each, the mean. And then we find the lower limits and the upper limits of the mean, the z factor and the P1 and P2 for 1 and 2 of their tests. So this is how our graphs look. This would be a fullest plot. The orange circle would represent the standardized mean difference of sum effect, and the yellow bars represent the 95% confidence interval. For our first model, the random effect model shows that there's a standardized mean difference of around 0.35 with a 95% confidence interval from negative 2.1 to 2.8. The fixed effect model, the standardized mean difference is 1 with a 95% confidence interval from 0.6 to around 1.4. The standardized mean difference is higher in the fixed effect model, showing that there is a larger difference between the elements compared in the first equations compared to random effect models. This is our second model. Here, the random standardized mean difference for random effect models is about 0.42 with the confidence intervals from negative 1.4 to about 2.1. For fixed effect models, we had a standardized mean difference of 1 with a 95% confidence interval from 0.7 to 1.3. Since the confidence interval is larger for random effect models, it means that it's accounting for more variance. That's why its standardized mean difference is also lower. And the fixed effect model has less variability, so it has a smaller confidence interval and a larger standardized mean difference. This is our third model. Here, the random effect model has a standardized mean difference of 1.9 and a 95% confidence interval from negative 1.6 to 5.4. For the fixed effect model, we had 1.3 as a standardized mean difference with a 95% confidence interval from 0.7 to 1.9. This is one of our outliers where the standardized mean difference of the random effect model is larger than the standardized mean difference of the fixed effect model. However, the confidence interval of the random effect model is still larger than the confidence interval of the fixed effect model. And so our last model that we did, the random effect model, showed that the standardized mean difference was 0.4 with a 95% confidence interval from negative 1.4 to 2.2. The fixed effect model showed the standardized mean difference was around 1 with a 95% confidence interval from 0.8 to 1.2. As before, the random effect model had a larger confidence interval and a smaller standardized mean difference. So what does this mean? It showed that for both models, it shows that the sum effect was greater than 0, meaning that Texel and DXI improves legend detection in both fixed and random effect models. Also, the confidence interval was greater in random effect models, showing that it's accounting for more variabilities in the data, showing that it can't narrow down its points. Additionally, the summary effect was smaller generally in random effect models, so a smaller effect size difference between the groups measured. So random effect models provide a broader insight by accounting for between study variability, and fixed effect models are better for more specific results. Each model has its benefits and negatives in certain fields. Fixed effect models perform better when there's little interstudy variance, and random effects models perform better when there's more interstudy variance.
Yeah, so our references, these are just basically like the sources we use. So the first one is the introduction to meta-analysis. That's like the site we use to just basically simplify what meta-analysis is. Our second one, that's the medical data set that we use, the TXI and photo imaging. And the last one is just the link to MATLAB, the program we used. And some of our future work is to like further test this program through MATLAB, apply some new equations on it, and also get some more medical data sets that we can test on. We want to create new models, not just fixed and random effect, to analyze the different types of data that we get from these medical data sets. We want to incorporate heterogeneity into these MATLAB models, and future expansion includes refining that heterogeneity estimation and applying the model to other studies. And yeah, that's it. We would like to thank Professor Zaidi at IntelliScience Training Institute for helping us learn what meta-analysis is and also help us conduct this experiment.
Thank you.